Hello everyone. In the last lecture, I have discussed about the algebra of subspaces. The first one was the linear sum, second one was the direct sum, and third one was the complementary subspaces. In the process of continuation of algebra of subspaces, today I will discuss two more points. That is the fourth point, disjoint subspace, and then identical subspaces. As the name suggests, disjoint subspaces are those subspaces of the vector spaces which when intersects they give only zero space. That is W1 and W2 on intersecting gives me zero subspace. Then we say that this W1 and W2 are disjoint subspaces. And identical subspaces, two subspaces U and V of the same dimension are called identical if and only if each is a subspace of the other. So these are two simple definitions of disjoint and identical subspaces which are complementary to each other. Now, based on the concepts of algebra of subspaces, today I will prove one very beautiful theorem, that is, if W1 and W2 be subspaces of the vector space VF, then V can be written as direct sum of W1 and W2 if and only if V is the linear sum of W1 and W2 and they are at the same time disjoint. So, students, you must learn this theorem as a statement also, that is, any vector space can be written as linear sum of two vector subspaces if and only if it is written as linear sum of that vector spaces and their intersection is the zero space. So firstly, actually this is also necessary and sufficient condition for a vector to be a direct sum of the two vector subspaces. So firstly you look, I will consider V as direct sum of W1 and W2. Then I will prove these two things. Before proving this theorem, you must be very clear about the definitions of all these things. So first I have supposed that V is direct sum of W1 and W2. Implies V can be written as W1 plus W2. Here it should be W2. Because by definition of direct sum, every vector of V can be written uniquely as sum of two vectors U1 and U2, where U1 belongs to capital W1 and U2 belongs to W2, which proves the first theorem. And this is a necessary condition also. Further, now I will prove that W1 and W2 on intersecting gives me zero space. For the short while, I am supposing that V is not zero. And if it is not zero, I am supposing that V belongs to W1 intersection W2. Also V belongs to capital V. Now you see, I am writing V in two ways. In the first way, I am writing V as sum of two vectors, that is 0 plus V, and at the same time also writing V as sum of small v plus 0, where 0 in the first representation, this 0 belongs to W1 and small v belongs to W2. In the second representation, I am supposing that V belongs to W1 and 0 belongs to W2. It means 0 belongs to W1 as well as V belongs to W1. Here V belongs to W2, 0 also belongs to W2, which implies that V belongs to capital V can be expressed in two different ways. These are two different ways, which is contradiction. Therefore our supposition is wrong. So 0 belongs to W1 intersection W2. That is, W1 intersection W2 is 0, which proves the second condition. This was the second condition. So I have proved two necessary conditions for a vector to be the direct sum of the two given subspaces. Now I will prove the converse part. For the converse part, what I will do, I will suppose these two things and then prove that V is the direct sum of W1 plus W2. To prove that V is the direct sum of W1 and W2, what I will prove that every vector belongs to, if it belongs to V, that can be represented in unique way. So I will start with the given condition that V is equal to capital W1 plus capital W2 and W1 intersection W2 is equal to 0, where W1 and W2 are subspaces of VF. Now you can take any small v belongs to capital V, then V is equal to U1 plus U2, where U1 belongs to capital W1 and U2 belongs to capital W. Now I will prove that the V is unique. This representation is unique. In mathematics, we generally take a contradictory approach. If possible, let this V can be represented in some other way, that is W1 plus W2, where W1, small w1 belongs to capital W1, small w2 belongs to capital W2. Now V is equal to W1 plus W2, but V is also written as U1 plus U2. From these two equations, I can say that U1 plus U2 is equal to W1 plus W2. On interchanging, I will get U1 minus W1 is equal to W2 minus U2. Since W1 and W2 are subspaces, so U1 W1 belongs to W2, implies U1 minus U1 W1 belongs to W1. This is the condition theorem I have proved while I was discussing about the subspaces. So whenever U1 W1 belongs to capital W1, then U1 minus W1 must also belongs to W1. Similarly, on the same ground, you can say that W2 minus U2 belongs to capital W2. Hence, U1 minus W2 minus U2, here it should be W1. Here it should be W1. U1 minus, yes, it is W1. Here it should be W1. Hence, U1 minus W1 is equal to W2 minus U2 is equal to 0. Implies W1 is equal to U1 and W2 is equal to U2. So any vector V belongs to capital V can be written in one and only one way, that is V is equal to U1 plus U2, where U1 belongs to W1 and U2 belongs to W2. Hence V is equal to W1 plus direct sum of W2. Actually, what I have done in the contradictory part, I have to prove actually that this V can be written as in one and only one way. But I have supposed that it is also written in some another way, that is W1 plus W2. But when I have approached it, I found that this was the contradiction. I cannot express V in some another way. Therefore, capital V is the direct sum of W1 and W2. That is the definition of direct sum. Hence, you have to now learn also that if W1 and W2 are the subspaces of the vector space, then direct sum of W1 and W2 must satisfy these two conditions. That is, it should be written as linear sum of two subspaces, and at the same time, on intersecting, they must give me the zero subspace. Thank you.